These are the Greeks, not the European populace though. Every financial option begins with a simple question. Given that option prices change every single day unpredictably, how much is it worth today? In previous videos, we've talked about the factors that change option prices. The current stock price, the time remaining, the interest rate, and perhaps the most mysterious variable of all, volatility. Today, we'll learn how sensitive option prices are to each of these factors. The sensitivity is called the Greeks. We can write this idea mathematically, given that it's a function and v is the option price. Let's look at the most influential variables. S as the stock price, sigma as the volatility, and t as time. Although they look straightforward with their definitions, we must ask ourselves, how much does each one of these matter on the option value? To answer this question, let's fortify our mathematical understanding of volatility first. Volatility. So what is volatility? Before understanding the Greeks, we need to understand uncertainty. Volatility measures how violent and sensitive the stock moves. High volatility means more violence and vice versa. It measures the violence using the randomness of investment returns. Imagine tracking a stock over several days. Each day it produces a percentage return, maybe down 2%, up 1%. To understand how erratic these numbers are, we first need a baseline, the expected value, or mean. Now we ask, on any given day, how far does the return deviate from that average? Mathematically, the deviation for any day is simply Ri minus mu. However, summing up all of these deviations gives us a problem. Positive and negative values cancel each other out, giving us 0, so we square every distance. Taking the average of these squared deviations gives us the sample variance, sigma squared. Variance is in squared percentages. We take the square root to return to original percentage terms. This final value, the standard deviation sigma, is the formal definition of volatility. But why do we use logarithmic returns? So far, we use standard arithmetic returns, but in modern quantitative finance, simple percentage returns cause a major mathematical headache. And it boils down to the simple fact that simple returns do not add. If a stock goes from $100 to $110, it gains 10%. But if it drops back to $100, that's a decrease of 9.09%. Add those two simple returns together and you get positive 0.9%. That's wrong. To fix this, we assume stock prices grow continuously via an exponential model. Taking the natural log gives us logarithmic returns. Because log returns are additive, two opposite moves cancel out perfectly to 0, making logarithmic returns the standard for financial modeling. Notice that volatility inherently depends on time. Daily price moves gives us daily price volatility. This is denoted by sigma, daily. To scale this up to an annual figure, you don't multiply by 252, the number of trading days in a year, because variances, not standard deviations, add linearly over time. Scaling standard deviations requires multiplying by the square root of time. Thus, annual volatility equals daily volatility times the square root of 252. However, real markets don't move in discrete daily steps. They trade continuously. To model this continuous randomness, quantitative finance uses stochastic differential equations, like this. Here, ds represents an instantaneous change in the stock price. The first term is the drift. It represents the expected deterministic return over an infinitesimal tick of time. The second term is where the magic happens. This is the stochastic component. Here, Wt represents Brownian motion, a pure continuous random walk. It models the unpredictable noise driven by news, earnings releases in human psychology. And finally, sigma scales the random walk. Now let's go back to the Greeks. An option's price depends on multiple variables: stock price, volatility, time, interest rates, and strike price. To see how the key forces work, we isolate just two inputs, the stock price and volatility. Now plotting option value against S and sigma creates a 3D pricing surface. Note that the sigma axis is the one behind the plane. Moving along the stock price axis gives us the Greek delta. Moving along the volatility axis gives us the Greek Vega. So let's freeze volatility to inspect a 2D cross-section of value versus stock price at 30%, for example. Hence, sigma will be 0.3. Now we have a 2D curve. The The slope of the tangent line at any point tells us how sensitive the option price is to a small move in the stock. From the slope as change in the option value over change in stock price. We take the limit as the price change approaches zero, which gives us partial derivative of option value with respect to the stock price. That slope is delta. Let's go back and look at the other Greek, Vega. Next, we freeze the stock price at $100 for example, and move along volatility. The slope of this curve measures sensitivity to volatility. This derivative, the option's value's rate of change with respect to sigma, is Vega, also a partial derivative. However, notice that delta isn't static. As the stock price rises, the curve gets steeper, which means that delta itself is changing. But how fast does delta change? To measure how rapidly delta changes, we take the derivative of delta with respect to the stock price. This gives us the second partial derivative of the option price, gamma. Gamma measures the curvature of the option surface and tells you how fast your delta position will shift. Returning to the full option function, let's turn our attention to time. By freezing all other parameters, we isolate option value strictly as a function of time, remaining to expiration. Plotting option value against days to expiration shows how time decay behaves. More time until expiration means more possible future price outcomes for the stock. As each day passes, uncertainty shrinks, removing potential outcomes and reducing the option's value. Moving along the curve toward expiration causes the option value to decay at an accelerating rate. The rate of value change per unit of time is expressed by the derivative of option value with respect to time. This derivative is theta. Because the options lose value as expiration approaches, theta is almost always negative for long options. For option buyers, time decay is a constant drag. Every Greek we've covered isn't just an isolated metric. Together, they form the core building blocks of the famous Black-Scholes PDE. A partial differential equation, or PDE, is an equation that relates a multivariable function to its partial derivatives, describing how a quantity changes simultaneously across multiple dimensions, like space and time. Building the equation piece by piece, we start with a time derivative, this theta, representing time decay. Next, we add the variance term scaled by half, volatility squared, asset price squared, and the second spatial derivative. This second spatial derivative is gamma. Then comes the drift component, the risk-free rate times stock price, scaled by the first spatial derivative, which is delta. Subtracting the risk-free return on the option's current value sets the entire portfolio balance to zero. Looking closely at the complete PDE, every term reflects a distinct physical behavior in the option portfolio. Notice that theta drives time decay. Volatility contains the wild randomness in the PDE. Gamma governs convexity and curvature. And finally, delta captures sensitivity to stock price movements. You might wonder, where is Vega in this equation? Vega isn't an explicit derivative term inside the PDE because volatility is a constant parameter of the system, not an independent variable. Vega measures how the entire solution surface shifts when that underlying volatility parameter changes. Parsing through these components shows that the Black-Scholes PDE is simply a dynamic balancing act between time decay, price movement, and local curvature. This equation perfectly describes how an option's value evolves in continuous time, leading to a crucial question: what happens when real-world conditions prevent us from solving it analytically? When we cannot solve the Black-Scholes PDE directly, such as with exotic derivatives, path-dependent options, or multi-asset instruments, how do we find option value? When there is no closed-form solution. Simply, we simulate the future using Monte Carlo. The stock price process is driven by two main components, but let's bring an old formula back first. The drift, which represents expected movements, and the randomness, which represents Brownian motion. Volatility, sigma, controls the size of that randomness. Simulating a single random path represents one possible future, But markets have thousands. That is not enough to yield reliable answers. So we use Monte Carlo simulation, the concept we talked about in the previous video. Assume we simulate a stock price against time, with volatility at 10%. Notice how many paths we have now? Now let's do the same thing with volatility at 40%. It all blows out of proportion. Volatility controls the size of the randomness. Volatility controls the width of those possible futures. To extract Greeks from a simulation, we remember that Greeks measure sensitivity. So we slightly change an input and measure the output change. For delta, we change the stock price, since delta is the partial derivative with respect to the stock price. For Vega, we change volatility, since Vega is the partial derivative with respect to volatility. For gamma, we measure curvature, since it's the partial derivative of delta with respect to the stock price. Finally, for theta, we move forward in time, since it's partial derivative with respect to time. If you want, we could delve deeper into the formula I just showed. Let me know in the comments. Now we understand Greeks. An option value v is not a static number. It is a multivariable function driven by the underlying asset price, volatility, time to expiration, interest rates, and the strike price. To navigate this multidimensional surface, quantitative finance relies on 4 core metrics of sensitivity. The Greeks are not predictions. They are the geometry of uncertainty. However, I've come out of my way and changed this from theory into exploration. I have built a web app called Quap that is run by an engine I made called QLab. By taking these partial derivatives off the page, we can interactively visualize option dynamics in real time, turning static calculus into an intuitive, responsive tool to visualize implied volatility, Monte Carlo, the option value, or these 4 Greeks we've talked about today. Although the lab is still relatively small, I aim to grow it and make it more practical than simply a graphical interface, as I learn more about applied mathematics, particularly applied mathematics using computer science, AI, physics, and finance. Feel free to check it out on my GitHub, link is in the description. This was the Greeks. In the next video, I'll upload a more philosophical discussion video, rather than a mathematical one.
What can you say when love goes away that hasn't been said before?